Welcome to The Explainer. Today, we are demystifying the modern API landscape. You know, if you've ever found yourself just staring at a blank architecture document, wondering exactly how your systems should talk to each other, well, you're in the right place. We're going to learn APIs in 10 minutes. Fun fact, over 80% of all internet traffic today is literally just APIs talking to each other. We're breaking down the essential communication paradigms, from standard web requests all the way up to cutting-edge AI integrations. I am incredibly excited to unpack this developer's toolkit with you, so let's get started. Okay, let's dive right into this. Here's our roadmap for today. We'll start with the modern API toolkit, look at REST as the reliable default, check out GraphQL for precision data fetching, WebSockets for real-time connections, webhooks for event notifications, and finally, MCP, the new AI API standard. But wait, before we look at our first tool, we need to bust a common myth right out of the gate. People often conflate API paradigms with asynchronous programming. But look, async await is not a communication pattern. It is simply how your server handles waiting. Every single time your code hits a database query, an HTTP call, or file read, it waits. Async await just ensures your server doesn't freeze all your other users while it's waiting for those I/O operations to finish. A massive trap to avoid here, calling synchronous libraries inside your async functions. Do that and you block your entire event loop. Keep that mental model clear as we move forward. All right, section 2, REST, the reliable default. Picture this. How do you build a SACCO or credit union member portal where users just need to check their loan balances and submit new applications? In this scenario, the client, meaning the user's browser, initiates all the interactions. Plus, the data isn't changing faster than the user can hit refresh. Because you're basically just building standard create, read, update, and delete operations, REST is absolutely the perfect fit here. Now, when you commit to REST, you really need to follow some hard rules in production. First off, REST can be highly cacheable, so you absolutely must add proper HTTP caching headers, like cache control and ETag. Second, always version your APIs right from day one. Think, /v1/orders. Because changing your data structure later, that will break your clients. Finally, use standard HTTP status codes correctly. Don't just return a 200 OK with an error message in the payload. Use a 201 for a created resource, a 404 for not found, and a 422 for validation errors. Moving on to section 3, GraphQL, precision data fetching. Okay, imagine an NGO platform. You've got field officers out in remote areas using 2G mobile devices, so they need incredibly lightweight data. But back at HQ, analysts on powerful desktop computers need massive, deeply nested data sets. With REST, you'd either overfetch data for the mobile users, completely grinding their 2G connection to a halt, or you'd have to maintain separate endpoints for every single device type. Total headache, right? Well, GraphQL solves this beautifully by offering client-controlled queries. Both the mobile app and the desktop app hit the exact same endpoint, but they pull exactly what they need in a single request. So the crucial point is that with this immense flexibility comes significant responsibility. You have to be super careful in production. You absolutely must implement depth limiting, otherwise a malicious or honestly just buggy client can send an abusively deep nested query that literally crashes your server and pages you at 2 a.m. Also, watch out for query recursion, where a query loops from a user to their orders, back to the user, and so on. Keep in mind, too, GraphQL doesn't cache well at the HTTP layer, and it is notorious for the N+1 query problem, which you'll want to fix by using a tool like DataLoader. Basically, if your service is super simple, don't use GraphQL just for the hype. It adds real overhead. Next up, section 4, WebSockets, real-time connections. So think about this. How exactly does a ride-hailing app track a driver moving on a map in real time? The driver's app needs to send GPS coordinates to the server every 3 seconds, which then instantly pushes those updates to the rider's app. If you tried to use standard REST polling at 3-second intervals for this, you would generate about 1,000 requests per single ride. That is a massive, totally unacceptable load on your servers. Instead, a single, persistent WebSocket handles this efficiently. It allows data to flow freely back and forth without the massive overhead of opening and closing HTTP connections 1,000 times. But WebSockets introduce entirely new production realities. Because these connections are persistent, they consume server resources continuously. You need to plan for horizontal scaling early on, which usually means implementing Redis pub/sub to share WebSocket state across multiple server instances. Furthermore, mobile networks drop constantly. You absolutely must handle WebSocket disconnects on the client side with exponential backoff for reconnections.
Lastly, implement heartbeats or ping pong messages to keep your connections alive. Otherwise, your load balancers will just silently close idle connections after about 60 seconds, leaving your users staring at completely frozen data.
All right, Section 5, Webhooks, Event Notifications. And this brilliantly illustrates the power of webhooks. Let's look at a real-world Kenyan e-commerce integration. Step 1, a customer pays via M-Pesa. Step 2, Safaricom's Daraja API, acting as the external service, proactively calls your backend's webhook endpoint with the transaction details. Step 3, your server securely marks the order as paid and queues up a confirmation SMS. It is entirely event-driven. You didn't have to poll their servers asking, hey, did they pay it yet? Over and over again. However, webhooks can lead to absolute disasters if they're handled poorly. First, always return a fast 200 OK status, as fast as possible. If you hold up the connection to do heavy processing, like generating PDFs or sending emails, the caller will assume you failed and will just start retrying the webhook. You need to push that heavy lifting to a background queue like Celery or ARQ. Crucially, your webhook endpoint is public. You must verify HMAC signatures so you actually know the data came from the trusted provider. And finally, build in idempotency checks. Without them, when the provider inevitably retries an event, you will end up charging your customer twice. And for sure, that is a guaranteed way to ruin their day. Okay, let's synthesize all of this into hard rules you can take back to your engineering team. If the client requests data on demand, use REST. If multiple clients need vastly different data shapes, use GraphQL. If the user needs live updates, specifically if your polling interval is under 5 seconds, switch to WebSockets. If an external service needs to notify you of an event, rely on webhooks. And underneath it all, when your code is waiting on database or file I/O, utilize async await so your server doesn't freeze. Let's move to Section 6 and see how this builds to our grand finale. MCP, the AI API standard. This brings us to MCP, the Model Context Protocol. You see, AI models have a fundamental limitation. Their knowledge is completely sealed off at the time they finish training. If you ask an AI about a file on your local machine or a row in your live database, it just can't natively see it. MCP is an open-source standard introduced by Anthropic that provides a standardized bridge between these AI applications and your external systems. It completely eliminates the need for developers to write fragile one-off custom adapters for every single new AI tool.
Think of MCP like a USB-C port for AI applications. It's a real game changer. Before this protocol, if you had multiple AI models in multiple databases, you were stuck building and maintaining a chaotic M times N matrix of custom integrations. By implementing MCP, both the AI host and your external service follow a shared protocol. It literally shifts the math from an unscalable matrix to a clean M plus N implementation.
So how does this protocol actually work under the hood? Well, the MCP client sits inside the AI application and coordinates requests. Your external system acts as an MCP server, exposing 3 main things: tools, which are callable functions allowing the AI to take action; resources, which are readable pieces of data for context; and prompts, which are reusable templates for standardizing tasks. The brilliance here is that your server exposes these capabilities securely without knowing anything about the specific AI model calling them. And depending on your security needs, these transports can run locally on your machine via Stadio or remotely across the web via streamable HTTP. Wow, we've covered a tremendous amount of ground today, from traditional REST endpoints to the real-time demands of WebSockets, and right up to the cutting-edge Model Context Protocol. Choosing the right tool for the exact shape of your data problem is exactly what separates good architecture from brittle, unscalable code. I'll leave you with this final provocative thought to ponder. As AI applications scale and inevitably demand access to your real-world data, will your backend systems actually be ready to plug into this new open standard of communication? Thanks for joining me on this explainer, and happy building.